This video will walk us through applying our colligative property equations for an electrolyte and a non-electrolytic solute. I'd like to just look at number 3 and number 4. Keep in mind, ladies and gentlemen, that you can have accessible your colligative property constant values as far as Kf and Kb, and you can trust that whatever solvent you are dealing with in the problem, that you will be given the reference quantities needed. All right, so let's take a look at number 3. To do these problems, I would have scratch paper, I'd have a periodic table, a calculator, and let's dig in. So number 3 reads and commands us to calculate the freezing point of a solution made from 32.7 grams of propane. Now, what we always have to be asking ourselves with colligative properties is, will this dissociate or ionize with the solvent? Well, what kind of solute is it? It is just made of nonmetals. It is not an acid. So this will not dissociate or ionize. So therefore, that Van Hoff factor is 1. Very important for us to make sure that we feel comfortable with moving forward. We are dissolving this solute in 137 grams of benzene. Okay, this is my solvent. It's in the greater quantity. The freezing point of benzene, which I would think is pure benzene, is 5.50 degrees Celsius. And its Kf is 5.12 degrees Celsius per molal. Okay, we are dealing with freezing point. So our equation is delta Tf equals IKFM. We are asked to find the freezing point, so we know we need to find the change in the freezing point and then apply it to the given freezing point. All right, so if we obey our equation, of course, the Van Hoff factor, because it is a covalent molecular solute, is 1. The Kf for benzene, remember, Kf and Kb values are per the solvent, given this in the problem. And remember, molality is mole of solute per kilogram of solvent. So we could expand that or simply just keep it as a lowercase m. Either of those would be fine. All right, and that's times the molality. But we were not given directly the molality. Okay, now we could go ahead and set it up here to solve for the molality, or you could do it separately and then plug it in. But I'm going to go ahead and do it within the problem solving, and I know molality is my mole of solute. What am I given about the solute? But I am given my grams. I need to get that to moles. So I would add up 3 carbons. Here's where, the aid of a periodic table, of course, is needed. So my formula mass is 44.11 in every 1 mole. And that will get me to moles of solute. And remember, it is per kilograms of solvent. I am given 137 grams. So I want my solvent to be in the denominator of my molality expression. So I have 137 grams of the C6H6, but I need that to be kilograms. So I am going to just do one more step of 1,000 grams in 1 kilogram and then chuck it out. So we will now have mole of C3H8 that will cancel this, and my grams cancel, and then my kilograms of solvent will cancel, and I will just get my degrees Celsius as my answer. So, quickly doing the math. And I get 27.7. Now, this is an experimentally determined value. It can limit our sig figs. This, of course, so we have 3, 3. This has 4, so we're limited to 3. I'm just going to double check my math so quickly. Times my 32.7 times 1,000. All right, and this is degrees Celsius. Now, here's where we have to apply our understanding. Remember, the colligative property is freezing point depression. We know that a solution has a lower freezing point than the pure solvent. The pure solvent's freezing point is 5.50 degrees Celsius. So pure benzene. Now, the benzene solution will have a lower freezing point. So what we need to do, because we've gotten a positive value for this, is to subtract this away. That will give us the solution freezing point. Remember, sometimes your KF values are negative, and sometimes they're not. So we need to apply our understanding of theory. And so what we get is our answer, and we want to respect significant figure rules for subtraction. We report to the least precise decimal place, to the 10th, to the 100th, so I report to the 10th. So the new freezing point will be negative 22.2 degrees Celsius. That is our final answer. All right, let's proceed on to number 4. Calculate the boiling point of a solution made from 227 grams of magnesium chloride dissolved in 700 grams of water. What is the boiling point of the solution? The KB, and we always know that our KB and KFs are per our solvent, so they're telling us the KB of water is 0.512 degrees Celsius per molal. Now, where's our pure solvent boiling point? Well, you are expected to know that the boiling point of pure water, and we assume 1 atmosphere, is 100 degrees Celsius. All right, so we are boiling. We know that we want to apply the change in boiling point equation. All right, first, Van 't Hoff factor. Well, what kind of solute is this? This is an ionic, so we know it will dissociate. So, in solution, you are not expected to write the dissociation equation, but just to give us confirmation of where I get my I value from. For every 1 magnesium chloride in water, it will separate the magnesium from the chloride ion. Remember, chloride is -1. We need 2 of them for every 1 magnesium plus 2. So I get 1 magnesium plus 2, but 2 chlorides, a total of 3 ions for every 1 magnesium chloride. My Van 't Hoff factor is 3. So to find the new boiling point, I just need to follow my equation. This is what I'm solving for. So I have 3 ions. The Kb value for water, 0.512 degrees Celsius per mole of solute per kilogram of solvent, or per molality. If you want, we could put, this over 1 and this over 1 so we can see how we're setting up the problem. All right, we are then needing our molality. Let's go ahead and find it as part of our problem solving. Molality is mole of solute. I don't have that. I just have grams of my magnesium chloride. So what I'll need to do is to get my formula mass, so 35.45 times 2 plus magnesium, 24.31, 95.21 grams of MgCl2 for every 1 mole of MgCl2. That will get me mole of solute, which will cancel there. And we know that is per kilogram of solvent. So the amount of solvent is 700 grams of water, but we need kilograms. And we know then that will cancel out kilograms, and then I'll get my degrees Celsius. So completing the math, 3 times the 0.512, all right, my first go round, I get 3 sig figs, 3, great. So 5.23 degrees Celsius. Let me just double check my math. Okay, fantastic. Okay, now that's my change in boiling point. So if the problem just asks for the change in or the boiling point elevation, this is it. But the new boiling point or the boiling point of the solution will be the pure solvent and its boiling point elevation. So we are adding the change. And look at that. We have changed the boiling point a little over 5 degrees. That's pretty significant. So you can see the possible impact of being an electrolyte or not. The use of magnesium chloride has 3 times the impact on the boiling point change than something like the previous example. So it's very important for us to be able to determine that I value.